Now it's my pleasure to introduce Michael Merzenich, Professor Emeritus at the University of California, San Francisco. He was trained as a neuroscientist at Johns Hopkins University and the University of Wisconsin before joining the UC San Francisco faculty. Research interests have included the functional organization of brain systems, the neurological basis of cortical plasticity, and the neurological origins and remediation of developmental and acquired impairments and illnesses. Dr. Merzenich has been recognized as the co-inventor of the cochlear implant. He co-founded Scientific Learning dedicated to delivering remedial brain-based therapies to help struggling school-age children. And in 2002, he co-founded Posit Science, which produces computer-delivered therapies to improve the brain health status of psychiatrically and neurologically impaired children and adults. So it's a great pleasure to give the floor to you, Michael Merzenich, and we're looking forward to the award ceremony tomorrow.
So I want to say at the outset that all of the research I'm going to talk about is team science. And I'm a member of the team. So I'm going to accept this award on behalf of this wonderful family of several hundred scientists that work with me directly, as well as the several thousand clinicians that have evaluated the effectiveness of the strategies that we've developed and trying to apply in the clinical and the educational realms. I also want to say at the outset that I'm going to talk about this in a very egocentric way. That seems to be the fashion in this meeting so far. But understand that thousands of scientists have contributed to the body of science that this work is based upon, and that has occurred in parallel, and that it could not have occurred without this incredible contributions of the broader scientific community, and this explosion of understanding of the operations of the dynamic brain. And finally, I want to say that I'm going to talk about a very, very complicated subject in a very, very superficial way. I want you to understand that about maybe a third of all publications in neuroscience relate some way or other to the plasticity of the brain. There is some relevance to them in what people are studying and reporting. And obviously, I can only talk in a very primitive way about this incredibly complicated scientific realm. So you can think of this as sort of skimming across the top of the clouds, sort of looking down and maybe every once in a while seeing something interesting. So that's the level at which we're going to talk about this in this presentation. 100 years ago, most scientists that thought about the brain imagined that the brain was continually changing itself as we improved in ability or as we acquired new ability. And actually, there were quite compelling experiments that were conducted more than 100 years ago that seemed to document the fact of adult brain plasticity. And even into the 1970s and 1980s, there were a group of scientists from physiological psychology that were studying plasticity to try to understand the basis of Pavlovian, what's called classical conditioning. And that's where the brain makes an association between a stimulus and a punishment or reward. And that punishment or reward is manifested by an expressed behavior. If the animal expects a punishment, then you see the animal cringe or respond in a way that indicates that they anticipate something bad is about to happen. And of course, that indicates that the brain in some way has grown an association between the punishment and the stimulus. If the stimulus, on the other hand, predicts positive reward, then of course, the animal, just like you would, in anticipation of that positive reward, indicates that it's forthcoming by your behavioral responses, which can be easily detected or demonstrated, as Pavlov did so beautifully in the early part of the century. And physiological psychologists actually demonstrated that the brain was changing in ways that exaggerated the expression of that stimulus or that reward or that conditioned response. But in the mainstream of neuroscience, the predominant view turned in an opposite direction. And there was a widespread belief 40 years ago, even 30 years ago, that the brain in an older animal was aplastic, something like the computer on your desk, basically hardwired. It basically had matured through an early developmental period, and all of its connections had become established in adult form. Every neuron basically now knew what to do. And we had to account for the amazing sort of evolution of behavior in an older life, because all of this was over with in very, very early part of life. We had to account for it by some unknown sort of mysterious algorithms in a brain basically that was fixed like that computer on your desk. And then we and others did experiments that demonstrated that the brain, in fact, was plastic on a large scale in adult animals. I'm going to try to describe these experiments in a simple way at the beginning. I say that our initial objective in the first experiments was to reconstruct the changes that occurred when a nerve that was damaged regenerated to reestablish functional connection between skin, because that's what a cut nerve does. If you ever had a damaged peripheral nerve, you know that it regrows back, and you recover some level of sensation in which you have some ability to locate sensation in the skin again. And this is really interesting because when you cut a nerve, it was demonstrated in beautiful experiments conducted in the 1960s that when the growth cones grow out from the proximal end of the nerve fibers, they move in a random walk across this gap. There's nothing that guides the direction of the movement. The surgeon generally repairs the nerve to ensheath it so it's within the walls of that sheath. But as it grows back to the peripheral nerve, it randomizes. So there's a randomization of the connections from the brain, you could say. What was beautifully ordered initially is now disordered, you could say shuffled. And nonetheless, there's some recovery of function after that. So we're very interested in trying to understand how that could occur. So initial experiments, we cut a peripheral cutaneous nerve, and then we looked in the cortical area representing the surface of the skin, cortical area 3B it's called. And this is in the brain of a monkey. We're looking down on the brain, lateral view. And there's a large representation of the hand surface. It's the most prominent area represented in the brain of the monkey. And in that hand representation, the other part of this area represents the other surface of the body. There's a very beautifully orderly representation of the skin, shown here very crudely schematically. The thumb more lateralward toward the fifth digit, the little finger more medially next to and discontinuous with the representation of the forearm, and the rest of the body, the palm below, more posterior. And on the bottom, there's another discontinuity in representation, and that separates the representation of the face from the representation of the fingers. Now, what we've done in this experiment is to eliminate the input from this critical, to us, very important surface in the representation of the body, the thumbward side of the volar hand, or the operational working surface of the hand. And what we expect in an aplastic brain is that it would sit there and wait for us to come back to it, or you could say sit there, unchanged, and ultimately it would be occupied, presumably reoccupied, with the recovery or the reinnervation of the skin as the cut nerve goes back into the skin and reestablishes connection with the receptors in the skin. But we didn't see that. In fact, what we saw in the initial experiments, which were conducted in the laboratory with John Koss and colleagues at Vanderbilt University, what we saw was that, in fact, when we looked at the representation of the hand, the regenerated nerve only captured a small part of its original territory, about a third. And the rest of this zone, formerly occupied by that nerve, was now occupied by topographically expanded representations of surrounding skin surfaces. So you can say there's movement into this area from the ulnar nerve, and it's beautifully topographic and progressive because we track the progression of this reoccupation across time. That is to say, this edge of the representation used to be over here, and the absolute location of everything across the zone of the skin has changed. Every location, as in the sense this is expanded into this now competitively ineffective zone. And so too has the whole substantial part of the representation of the ventral face moved into the former territory formerly representing the surfaces of the hand. Most of the rest of this territory is occupied by inputs that come in from the back of the hand. And then when the nerve goes back into the skin, and again completely extended across the skin, it recovers only a part of that territory again. And everything again is shifted in location back from this intermediate stage in which all of this occupation is occurring. And when we look in this zone at any location, we see that at any given sample site, there's a beautifully limited receptive field. Neurons respond only to a very limited piece of skin, just as they do in the normal representation of the hand or any other part of the body. So it's reestablished very beautifully localized responses, even though it's occurring presumably with the shuffled input, because what we expect to see was very weak input from all across the skin surface, giving that shuffling anatomically. Not only that, but next to this, any given sample site, we might look at a site adjacent to it, and we see that it actually represents an adjacent region of the skin, and it doesn't move in any predictable direction across the surface at the height of the animal. It could go north, south, or east or west. But it's reestablished the topography. If we look at the next site, it's likely that the receptive field will be adjacent to it. And actually what we find is a small zone, a little patch, in which a significant little patch of skin is represented topographically in a highly ordered way following this manipulation. Across this boundary, there's a discontinuity. And across this boundary, we see other little patches of skin that are represented in other locations that represent other little locations. So we have a kind of patchwork, a patchwork representation of different patches of skin, a completely beautiful order constructed in a completely new way from the shuffled input. I don't have time to go through explaining how this led us to understand how the brain was obviously massively plastic. But we can see from this that the adult somatosensory system is plastic in these adult animals. And I might say one of the first things we did was to through consultation with people in the vivariums at National Institutes of Health, acquire an animal near the end of life to try to determine whether or not equivalent plasticity would be seen near the end of life. And we saw that it was. Well, this plasticity is in place, you could say, for life. We could see that with nerve regeneration, there's a remarkable emergent response selectivity. So neurons shouldn't be so beautifully selective, so much like they are in the normal case, but it's obviously emerged in some way from changes that occurred in this system as a consequence of its plastic remodeling. And we also see emergent new topographic order, which is really interesting. These progressive changes are, we believed, an almost certain product of competitive and coincident-independent, what we call Hebbian network plasticity. I emphasize the phrase Hebbian network because we know that this competition in the cortex has both excitatory and inhibitory terms. We believe that inhibition spreads across the horizontal dimension of the network farther than excitation. And you could say that in a competitive network like this, two things are happening, and speaking very simplistically. First of all, the excitation and heavy engagement of a particular source of input is competitively weakening whatever inputs are normally dominating neurons in the surrounding territory. And at the same time, those competitive inputs are strengthening the ability of that neuronal population working cooperatively to capture the neurons on its border. So that's the essence of the plasticity that we believe we were witnessing in the cortex. In detail, cortical mini-columns, these cooperative groups of neurons that are representing together, coupled together to represent together, each of these little pieces of skin. An orderly representation of the body surfaces indicated by these experiments are time-based constructs, subject to continuous plastic revision, and not fixed or immutable anatomical constructs as they were conceived to be at this point in neuroscience history. Cortical representation and recognition processes on the basis of this simple experiment must be relational because they have to tolerate the fact that we can remap the skin in a substantially different way. without a confusion about the locations of stimuli from the skin or the reconstruction of images felt on the skin through this period of recovery. We quickly confirmed that heavy network plasticity accounted for the plasticity phenomenology we recorded, and the first experiments we did simply involved conducting a procedure in which we fused two fingers together and demonstrated that the normal discontinuity between the representation was destroyed by that fusion. And now, across the line in which the two fingers were fused, we saw receptive fields that extended across the scar line where this artificial, where the syndactyl condition had been created. Clearly, coincident, codependent integration that had occurred. And in another way, we eliminated the inputs from two fingers. We saw everything from the surrounding palm grow in and completely occupy the zone and create a new boundary because of the substantially non-coincident inputs that are occurring now in these remote fingers. We also demonstrated it by showing that we could move skin a relatively long distance across the hand by using an island pedicle graft with the innervation and the vasculature intact. Move skin from the outside of the fourth finger onto the inside of the thumb, transferring the skin innervated from this surface back to the outside of the fourth finger, and waited a few weeks. And the consequence of that was an integration of the representation of this skin, which anatomically should belong way across the map, into the topographic representation of the thumb. Now we can move across the thumb, right across the scar line, and when we reach the scar line, receptive fields integrated information from across the scar line. We can anesthetize the nerve innervating this side of the hand, and we cut those receptive fields in half. Or on this side of the hand, and we cut off the second half. So this is obviously coincident-independent co-selection or co-strengthening of synapses are accounting for this. We also showed that plastic remodeling could be faithfully reproduced in computational models. So there is a history of creating these models in so-called theoretical neuroscience, not terribly theoretical at this point. It's gotten more theoretical since. But we were able to simulate most of the phenomenology that we recorded earlier in these models. And then finally, we repeatedly showed that these rules are reliably expressed in behavioral experiments, where we manipulated the locations and the time structures of inputs driven into these networks in an organized behavior in progressive training. The bottom line is that we soon understood, to a first level of understanding, how to change the processing and machinery of the brain within the limits of these rules at will. Now here's a very simple experiment that we did in this period, in which the monkey was trained at a behavioral task, in which we were trying to improve its ability to make accurate distinctions about the temporal features of stimuli by delivering stimuli down on the surface of a finger. And in this first version of the task, we deliver the stimulation always in a very localized form to a specific and unchanging location on the tip of a finger. And what we saw as a consequence of this is that this location of the finger was a competitive winner. And it won by enlarging its receptive field. It got bigger and bigger and bigger, and pretty soon, it extended all across the tip of the finger that we engaged in the behavior. We now saw that in the cerebral cortex, every neuron across the horizontal distance of about a millimeter had the absolutely same identical receptive field. And again, this is a consequence of a competitive winner in a competitive heavy network. The estimated neuronal membership for this giant column was about 10,000 neurons. And now we changed this experiment. The behavior is exactly the same. The animal's making the same distinctions. But now all we do is in every trial block, we simply move the location of the stimulation. And now every little point in the skin is a competitive winner. And a very different thing occurs. Now receptive fields are smaller than normal. And now cortical columns are smaller than normal. And now estimated mini-column membership was in the order of 100 neurons. A radically different result occurs as a consequence of manipulating information. In this case, just by manipulating where correlated information is delivered into this network by place. So in two groups of animals trained at the same task One had profoundly degraded its ability to localize or discriminate spatial aspects of stimuli in its distant finger, and the other had improved it, substantially improved it. I could take any one of you and relatively easily through training improve the ability that you have in discriminating or distinguishing felt stimuli on your finger or your hands or anywhere in your body. Or I can take any one of you and degrade it. I could take any one of you and, by the application of this rule, destroy your ability to understand what I'm saying. Okay, maybe some of you would enjoy that. Or I could take any one of you and improve your ability to understand what I'm saying under difficult conditions. Plasticity is a two-way process. You can drive changes very naturally by training in a positive or negative direction. Now, here's an exaggerated form of this experiment that was led by Xiaoxing Wang, who's now a professor at Johns Hopkins University in biomedical engineering. And the experiment is very simple. We basically have a very light, narrow bladed stimulus that's striking across 3 fingertips, always in the same location, or 3 finger bases. And the animal's task is simply, the stimuli is moving back and forth across these fingers. And the animal's task is just to determine when 2 strikes occur in a row, either on the finger bases or fingertips. So back and forth, then 2 strikes, the animal detects that and responds, is rewarded for responding, or maybe 2 in a row on the finger bases. So that's the task. And as a consequence of doing that for a few weeks, there's a dramatic change in the way the surface of the hand is represented in the brain. Now here we see these large red areas, and everywhere across it, every neuron responds to very large receptive fields on all 3 fingertips. So now we have a huge assembly of neurons operating as a cooperative sensation. Very reliably, every neuron, in a sense, representing the same large skin zone. So we completely de-differentiated, you could say, the representation of these large areas of the skin. Same with the finger bases. In between, this dark band represents the invasion of a non-participant in the competition. And that's input from the back of the hand, never normally seen there. It's there because the inhibition from these 2 strong competitive cell assemblies are disallowing the representation of anything near my to occupy it. And someone not so directly involved in the competition is advantaged and moves into this weakened, it takes advantage of this weakening and moves into this territory. Now, one of the very interesting things about this experiment is that by this training, the monkey lost control of its hand. Even we realized that it was no longer, after a while, several weeks, using this hand for anything. And pretty soon the monkey comes in and puts its hand on the appliance that we use to position and deliver these stimuli in a reliable way. And as soon as it touches the appliance, the hand is thrown off. We had generated in the monkey what's called a focal hand dystonia, which is a common human condition, applies to millions of people in the world, in which the functional use of the hand is destroyed by hand use. And what's destroying it is a de-differentiation that's temporal coincidence-based. So if you use your hand in any behaviorally attentive way, and you drive inputs into relatively large surfaces of the hand, you can anticipate that ultimately the feedback power for any contact to those surfaces of the hand will be so great that the feedback gain in a loop controlling movement is greater than 1. As soon as you engage it, the brain goes into oscillation. It'll take several minutes for it to calm down before you can initiate any movement. This is an acquired condition. It's a failure mode. It's an expected failure mode of a self-organizing brain. It's one of many. But doing these experiments made us realize early on that the brain has failure modes that we could predict. That we can begin to think of almost any psychiatric condition, and we could say, well, how could the brain move progressively in a way, change itself in a way that it loses control in its critical aspect, become distorted in this way? And in a sense, every psychiatric illness represents a form of failure that you could predict to rise from a machine like this that organizes itself and it's powered. So We conducted further studies of one key aspect of the process, plasticity process, I want to talk a little bit more about, and that's the reversible or bidirectional nature of plasticity. So one of the ways we studied this is by making comparisons of brains of animals near the end of life, and subsequently of humans near the end of life, and then comparing the characteristics or aspects of the brain that are relevant to its function and health with the brain of an individual in the prime of life. We also compared the brain of rats that have had a very lousy early life, you could say a difficult, challenging early life that leave them compromised, to an animal that's had a normal, healthy early life. Now, what we did initially in these studies was to look at about 20 things and ask ourselves, well, how many of these 20 things, and I'm going to show you some of them in a minute, differ in a brain that's really struggling from the brain that's obviously doing well? And the answer is all of them differed, very significantly. Then we ask ourselves, well, how many of these things that differ advantage the older brain? And the answer is none of them. In every way, younger was more reliable, more powerful, more obviously intact. Older brains in general, in whatever we looked at, were the losers in the competition for who had the best. And then we ask ourselves the more important question: if we took struggling individuals, in this case initially in rats, into training, if we sent them to the brain gym, which of these characteristics could we drive in an improving or corrective direction? And the answer to that question was all of them. All neurological abilities appeared to be substantially, if not completely, restored. So here's some of the things that we looked at: local and long tract myelination, brain response power, brain response dynamics, coordination, forebrain system connectivity, cortical mini-column sizes and boundaries, physical and functional integrity of specific neuronal populations. We've looked at 4. Chemical receptors controlling synaptic communication and plasticity, topographic orderliness or precision, response selectivity, accuracy, reliability, growth factor expression and function, and on and on. Everything we look at is degraded in the older or the challenged brain, and everything is improvable by intensive forms of training. You can say, well, how complicated does the training have to be? The answer is not very complicated. It takes training in 2 forms. Training in 2 forms. So here's a few examples. We're looking down at myelin-based protein. I'm sorry for the lighting in here. It's not very. You can see that this is indicating the formation of new myelin. You can see that there's a significant, ongoing, healthy regeneration of myelin, compromised in an old brain, restored by training in a young brain. And if we have the dosing right, completely restored. Here's the second example. We're looking at local response correlation. A correlation is a function of cortical distance, and these are from big averages across big samples across the brain. Here's the older brain. Here's the brain that's been trained, and we actually have to train the young brain to bring it up to a level above the older brain. Here's BDNF expression, and this is from a study in which the animals were struggling because we compromised them in early life simply by giving their mother an antidepressant drug. And they received the drug through nursing, and as a consequence, BDNF is downregulated. In an older brain, we'd see losses that come to about 1/3 to 1/2 of the normal level. In both cases, they're almost completely restored by training. Here's another example. This is a specific population of inhibitory neurons. These are part of inhibitory neurons. And they're richly expressed in the young, healthy brain. Very relatively sparse in the older brain, and their numbers and integrity and morphology are substantially recovered by training in the old brain. Here's the noisiness of the brain, in which the animal is making a distinction between this is background noise activity. This is actually the responses to a meaningless, ongoing, unchanging stimulus. And these are stimuli that are exceptional to it, not it. And you can see there's lots of confusion wherever these oddballs occur. And here's the brain of, and we see, this is what we'd see in a normal young animal, and here that we're looking in a trained animal, and we see a complete recovery. He looks just like a normal animal, with a beautiful separation between these unexpected stimuli in the background. Here's another example. These are serotonin transporters, and this is one of the number of ways in which we looked at the recovery of modulatory response machinery of the brain, and we see that it's healthy in the normal case, down in the impaired case and recovered substantially in the trained case. And here's the power of inhibition. We can see an old brain, which things are very much weaker than the young. When we train the old brain, we actually have to train again the young brain to move it past in its power, the old trained brain. And here's an important extension. Things are not happening, are not just limited to, you could say, the connective neurology of the brain. Here's one of the criteria that we use to define the status of the neurovascular unit. And here we're looking at the integrity of what's called the blood-brain barrier, the separation of the compartment of blood and brain tissue in the brain. That's important because blood in brain it increases the local excitability wherever leaking is occurring. And leakage is a problem in old animal and human brains. You can see there's a lot of leakage, completely restored to normalcy by training. We also see such changes in reactive hyperemia, that is to say the control of blood flow, that's a function of the local activity in brains, very degraded in old brains, especially in what's called the default network in human brains, and substantially recovered by simple forms of training in old and in otherwise struggling brains. So these 20 or so aspects of physical and functional brain define the functional competencies and the health of the adult brain. And we can see that they're all bidirectionally plastic. And note that in struggling brains, all are substantially restored to a higher functional and healthier adult status by simple forms of progressive brain training. So how do I turn a struggling brain into a more capable, that is to say a, quote, younger or more capable one, a more normal one? Well, I train it. Of course, it matters how you train it. So how can you turn the brain in the prime of life into an old one? It turns out that's very easy to do. All you need to do, in fact, is to just add noise. And you can add noise by manipulating the inhibitory process in the brain so everything, the background excitability level comes up. You can add noise simply by managing a life of an animal so it's always in the presence of continuous environmental noise. Both work. So an animal in the presence of continuous acoustic noise, delivered on a level, for example, in which it doesn't ever damage the hearing of the animal, but it's always there at a relatively high and obnoxious level, adding lots of chatter into the machinery of the brain. And in a few weeks, the brain looks like the brain of an animal near the end of life. So you could think of the evolution of the brain as it advances from its infancy towards the peak of life, in the middle decades in the case of the human brain, as being a sort of anti-noise adventure, where the brain is organizing activities on the basis of the time structures and the locations of inputs delivered into these networks, reaching a peak, operating with its greatest powers, at its highest speed and reliability, its greatest resolution of information in the peak, and then noise creeps into the machine, and it goes right back where it started from. But this process is, by its nature, reversible. It's designed to be reversible, to go forward or backward. And why is it designed to be reversible? Because the brain is actually controlling all of this on the basis of outcome. It's controlling it on the basis of outcome. When it gets the animal to answer right, and whatever it's resolving or trying to do as an adult, it advances the machine and its characteristics. When noise creeps in and it makes more and more mistakes, you could say, it moves the machinery backward in a way in order to sustain it getting the answer right, because getting the answer right is critical for its survival. It's important to know that going forward in infancy and childhood is neurologically equivalent to going backward through training in old age. And one of the striking things about these experiments to us is that the brain of an animal near the end of life is very much like the physical and functional brain of an animal at the beginning of life. So what evidence do we have that shows that this human brain plasticity is equivalently bidirectional? Well, we can look at almost any characteristic, like the brain's speed of bited attention. How fast is the brain operating as a processor, which is an index that all of these things have changed in a positive direction in an animal brain. And just as in an animal, we can see a deterioration from the 20th birthday, you could say, to the 100th birthday, very systematic change in the speed in which the brain is operating, which means that all of these characteristics, or many of these characteristics, have changed together in a degrading direction. But when we train the animal, train the human, we see almost equivalent advances in processing speed for humans of any age. So this is a roughly equivalent dose of training for animals of age ranging between 20 and about 90 years of age. And if we look at people from their 75th birthday going back to their 20th, we can see that the trained human is actually superior, equal to superior in ability on the average to the untrained 20-year-old. And we see that over and over again. In fact, we see that on almost every characteristic that we evaluate by training. Here we train humans. I could show you 30 or 40 of these plots. They're all the same. In every case, older is poor. Older is poor. Upper four panels, poorer is up. And the lower four panels, poorer is down. In every case, we have strong training effects at every one of these sub-skills. In every case, we can move it. In this case, we're moving back from the 65th birthday. And we see the performance is equal to superior after this equivalent period of training to the performance of an untrained 20-year-old. So what changes when the brain struggles? Everything. And what can be reversed by training? Well, everything can be reversed. Kind of good news, isn't it? So on the path to harnessing the GD, we also extensively studied machinery that controls change in the adult brain. And I'm out of time, so I'm not going to say, but just say these are just fabulous experiments. And they show that was a joke. They show that adult plasticity is controlled as a function of behavioral state and outcome. Of course, adult plasticity is not chopped liver. It's purposeful plasticity. The brain only permits change when it's to its advantage. That's what it's up to. We move from a period of chaotic anything goes change in the baby to change that's under the brain's own control for its own advantage. That's what it's up to. That's what adult plasticity is all about. It's not modest. Different modulatory systems operating with different time constants and via different processes nuance brain change. The machinery that controls brain change is itself plastic, and one of our overriding goals in almost every therapeutic use of plasticity is to drive those changes in the machinery that's controlling plasticity itself. And finally, we and others have defined on the sort of first level the rules that apply for this learning control machinery, so we can actually drive learning in the brain of an older individual, an individual of any life, and any struggling or normal brain with high efficiency. So our conclusions are that the brain is plastic for life. We know the rules on the first level, and within the limits of those rules, we can change the operational brain at will. The acquisition or improvement of our abilities is a product of adult plasticity. Experience-driven plasticity defines our operational personhood. We actually revised our brain by use in all sorts of ways that really defines our operational capabilities in detail. The practical implications, of course, are that psychiatric illnesses are failure modes of our self-organizing brains. Expressions of neurological dysfunction and illnesses are also largely a result of negative brain plasticity. Plasticity is just adjusted to make the most you could say out of its struggling, noisy conditions. Both are hypothetically correctable via training. We understand how to control the gene for potentially great human good. So who in the world can be expected to be able to help by the application of this science? And the answer, of course, is everyone. So on these bases, I left the laboratory at the University of California, and I focused on trying to translate this science into medicine, into education, into the world. At first, I began with working with Paula Talal, who's a professor at UC San Diego, William Jenkins, a former colleague, Stephen Miller, colleague of Paula Talal's, and to establish Scientific Learning Corporation, with obviously critical help from people from the business side. And there we developed and applied its fast-forward game-like computerized training programs. And our goal was to help several million children overcome impairments, frustrating their oral language, reading, and broader scholastic success, and help children that had difficult childhoods overcome it, and to help hundreds of thousands of non-English speaking children more rapidly acquire English language skills, and to help improve the capability of hundreds of thousands of more seriously developmentally impaired children. So we trained a total of about 7.5, 8 million children using these strategies. Most children struggle to read or struggle academically, are restored to the ability to read and read at grade level or above, with not so many hours of training. Then I later co-founded Posit Science with Jeffrey Zimmerman, who's in the audience, where we deployed brain plasticity-based training, and we had the goals of preventing and treating mental illness, preventing and helping people overcome their many addictions, helping restore environmentally damaged children and adults to a human family, helping children and adults overcome losses resulting from concussion and various things that damage brains physically, sustaining and managing brain health to prevent dementia onset. There are strong impacts in delaying dementia impact by intensive training, blocking a progression to Alzheimer's disease, Parkinson's disease, Huntington's, improving workforce efficiency and quality, and growing brain power. I'm almost done. So, the translation of neuroplasticity science out in the world for the benefit of humankind shall transform brain health medicine. There's no question about this. The brain has tremendous powers to correct itself if it's guided in an appropriate way. It will is greatly enriching educational practices and help us all find a way to a more effective, safer, and more fulfilling and longer passage in life. And perhaps just as importantly, the science resolves age-old arguments about our natures and about the origins of our personhood. And as we evolve in our life, as we move across the life, we're actually creating a machinery in our brain that's all our own, massively specialized in an individuated way through quadrillions of transactions, moments of change, incredibly, wondrously differentiated by where we are in life and how we expend life. And so we are all truly extraordinary and marvelous works in progress. And I strongly suggest to everybody in the audience to make the most of the greatest of personal endowments in your own life. Thank you very much.